Well, good morning, everybody, and welcome to this webinar on, turn off my monitoring devices here. Welcome to this webinar on LLC converters. Sorry, technical difficulty here. All right, we have many hundreds of people in the room right now from all around the world, so welcome everybody. I hope you're doing well, and I hope I can entertain you and maybe teach you something over the next hour or so. A little bit of administration. If you click on handouts on your GoToWebinar, you will be able to download a copy of the presentation in PDF form. You can also download it in PowerPoint form, so you can actually click through the PowerPoint presentation as you will see it go today, which is nice if you want to show somebody else what we're doing here. We also have a copy of manuals there if you want to get the RidleyWorks manual that explains how the LLC works, and also the RidleyBox manual, which is available for you to look at as well. So again, welcome to everybody. My name is Ray Ridley. For those of you who don't know me, it's been about a year since I presented a webinar. I think even more than that. We had Nicola Rosano doing the dual active bridge converter about a month ago. So this is the first one that I'm coming back to present here, and excited to be doing that and talking to everybody again. And the topic today is LLC design. And I'm going to show you what we've been doing on that for the last almost 3 years now. LLC design is actually quite well established, but as you're going to see when we go through the details here, it's the details can become quite complex, and that's what we spent a couple of years working on to get a package ready for you that could design this LLC very quickly. So let's get started. Before I go into the technical material, a couple of acknowledgments for you. One of them is Art Nace, who I've worked with for about 30 years. He's our longest user of RidleyWorks out there in the field, used it in aerospace applications many times. And he also did all the programming that moved us from doing the design of the LLC and all our other converters that we cover directly into LT Spice. So an enormous amount of details and management has gone on there from Art, and I greatly appreciate that. This is what you get to do when you retire. You can't stop. You have to keep designing. You have to keep writing software. That's what you do, and Art does that exceptionally well. I'd also like to acknowledge Nicola Rosano. Nicola did the first LLC presentation that we recorded a couple of years ago now, where he developed the impedance curves for designing LLCs the easy way. There's a fair amount of controversy about that. Not from my side. I mean, to me, that's the way to do it. But his approach is just do the complex math once, and then when you've got a core design or kernel design, as he called it, then you just scale it for frequency, voltage, and power. And of course, those concepts came from Sanjay Maniktala, who developed those and also worked with Nicola Rosano. So if you're looking for the background of LLC design, I would encourage you to go watch the video that's it's actually linked in your download. If you download the PDF or the PowerPoint file, you will see the video that we recorded on, you know, all the technical details, all the equations on how LLC design actually works. So that's really solid background for you, and I'm not going to repeat that here. Don't think it's necessary. Hold on a second. Some feedback going on here. Hopefully that's better. Okay, so that's Nicola and Art, and they're both on this webinar, I know. So if you have questions, we can pass those on to Nicola Rosano, and Art Nace is here as an organizer as well. Let's see, LLC. It's a new topic for many of you. You've probably heard of it. Many of you, I think, are probably thinking about using it maybe for the first time. And I've been looking back over, my career and things I've done in the past, and it occurred to me a couple of years ago when I started really working hard on the LLC to automate the design that I actually did my first LLC back in 1980. At the time, I did not know that I was designing an LLC because nobody had named it that at the time. So it didn't get called an LLC, but it has all the characteristics of it. You've got two FETs here. And being 1980, when I did this was actually two bipolar transistors, and they were switching at about 30 kilohertz. And then it's got a resonant tank, a transformer, and then a capacitive load. So this is not the LLC that you might recognize now because it doesn't have the diode rectifier on the output. But as you can see from the schematic here, it had an L and another L and a C, which makes our LLC. And the difference is, we're not rectifying and forming DC. This project that I was involved in was designed for an AC output at the switching frequency. And it was quite a challenge. Number one, because I'd never done any power electronics before. I was just thrown into a lab in the basement of Boston University and given this project to design. It had 170 volts coming in, which is the rectified AC line, so it's plugging straight into the AC line. And then I was switching these two transistors. I had no idea how to drive bipolar transistors at the time, so I just kind of hacked up a circuit to do that. And then there was a transformer which had leakage inductance, had magnetizing inductance, and the series cap, and it operated above resonance. Now, some of you may say, okay, well, that's a pretty simple circuit because you don't have the diodes and it's not non-linear. But to make up for that, somewhat simplification, the output voltage that I was dealing with was 6,000 volts AC. So that was a challenge, especially in the hands of an undergraduate student who had no idea about corona and breakdown and winding transformers. But I learned so much in those days. There's still aspects of that converter that I teach today. And so that was one complication. How do you wind a transformer with 6,000 volts on the output? And the other complication in this circuit was that the magnetics were designed to saturate. So during the resonance cycle, one of the magnetic elements would go into saturation. And the point of this was to create a ferroresonance circuit running at 20 kilohertz that would automatically regulate the AC output. So that was an incredible nonlinearity in the system. And the unique thing about this converter was that it would provide regulated AC output with no feedback around it. So as the input line moved up and down, the output would always regulate the AC output. And that's the characteristics of ferroresonant converters. Now, why is this important? It's not what you're going to build if you're an LC. Is, well, when I was winding these transformers, they would fail on a daily basis because I didn't know how to get around the 6,000 volt corona issue until much later into the project. But something that never really failed very often was the bipolars on the primary. Even though I was switching 170 volts and I didn't really know what I was doing in terms of speed of turn on and turn off, one of the characteristics of the LLC is that it gives you soft switching on the primary FETs or bipolar devices. So these devices will turn on when the voltage across them has collapsed to zero. So you get zero voltage switching. And I'm pretty sure, looking back now, that that's why I didn't see these transistors failing as much as I would expect them to. because when you're processing, that kind of voltage and you're coming off an AC line, and you don't know what you're doing very much, certainly at the beginning, you would expect these devices to be failing on a regular basis. So zero voltage switching, that was my first exposure to it. And it worked very nicely, and the whole circuit was really interesting. It gave me about a year of enjoyment playing with the circuit and winding transformers, and that really formed the basis, my foundation in magnetics design, where I learned you've got to sweep the magnetics over the frequency range. You've got to find out where the resonances are, and then with an LLC, as those of you with some experience will know, you choose to operate the LLC above the first resonance of the circuit, and that's how you get the zero voltage switching on these two devices. Here we are 40 years later, and every serious contender for high efficiency, high density power is now zero voltage switching on the main input FETs. You can do it with the LLC, you can do it with many different topologies, but if you're going to play into the future, zero voltage switching is what you do. So that was a interesting background for me. I've always thought this would be a great problem to hand students today, but it's probably a bit too much, to be honest. But interesting. Where are we today? Well, we've got LLC circuit variations in that we put into RidleyWorks. That's our design package. And the most common one that you will see is the half bridge inverter on the primary. All right, so these can actually be packaged FETs. They can be GaN FETs if you want, where these can switch very fast and very efficiently. Then you got the series L, series capacitor, the transformer, the magnetizing inductance. And the most common application on the secondary is to do a center tapped output with two secondary windings. And that's just because most people doing LLC are doing relatively low output voltages. So the center tap reduces the stress on the two diodes and lets you optimize this secondary better. Notice the somewhat unusual drawing of the secondary diodes. Of course, in the real circuit, we're not going to use diodes. We're going to use synchronous rectifiers. And if you connect them this way instead of on the other side of the transformer winding, which is the conventional layout for the half bridge circuit, then you're driving these synchronous rectifiers with respect to ground. So if you're doing half bridge circuits, if you're doing LLC circuits, move the diodes. It applies to the forward converters, everything else as well. So that's the most common half bridge variation of the LLC that you'll see in the market. The next version of it, if you have a high output voltage, it becomes useful to replace the center tap secondary with a full bridge layout of the diodes. Now you've got 4 switches to control on the secondary. It gets a little bit harder because these are with respect to the positive output, but same circuit. Here's a full bridge primary, so as power levels go up, if you're getting up around 500 watts or more, you may design a full bridge on the primary to share the stresses on the switches. And here it is with a half wave rectifier. And then you have the full bridge inverter on the last one, and then this is for a higher voltage output, the full wave rectifier on the output. So there's something interesting on this circuit is that if you attended Nicola's presentation on the dual active bridge converter, the LLC circuit is actually indistinguishable from the dual active bridge circuit, assuming you replace these diodes with active switches. It's the same schematic, and it's just a question of what are the values of the L, the coupling cap as it would be in a dual active bridge, and then the magnetizing inductance. But the schematic is the same in both. So that's kind of interesting. And now a lot of people are moving on from the resonant circuits like the LLC onto the dual active bridge. And all the reasons for that are covered in our most recent webinar by Nicola Rosano. Okay, so go watch that if you're interested in moving forward with the dual active bridge. By the way, if you have questions at any time, feel free to ask them. And we've got several people here answering the questions. If you're having trouble with audio, it's your end, because we got about 400 people online here, and there's just about 3 of you asking about the audio. So it should be good. Okay. Somebody asked, yeah, what was the load current at 6,000 volts? It wasn't much. It was for what they call a static eliminator bar. It was for spraying static across paper in a copy machine. But it doesn't matter if you have a lot of current, a little bit of current. It's 6,000 volts. It's 6,000 volts. It's a good place to start if you want to be serious in power electronics. Okay, everybody there. I'm sure we have some academics on board, and any LLC presentation, you know, is not really academic enough unless we say a few words about first harmonic analysis. So this is the basis of the design curves that people produce. So I will follow convention here, and the industry people will groan because they don't like first harmonic analysis, and the academic people perhaps will go, oh yeah, first harmonic analysis. So my few words about first harmonic analysis are, you don't need to do this, okay? You don't need to do it. Okay, if you're putting first harmonic analysis in your LLC design these days, you're reinventing the wheel. If you're writing a paper on LLC, fair enough. If you want to get the paper accepted, maybe you have to throw some complicated equations in there. But the work that Sanjaya Maniktala did and Nicola Rosano did was to solve this problem for one circuit, and then say, okay, that's it, you're done. No need to go back to basics again. Let's just use our design and scale it to whatever your power level is, whatever your voltage level is, and what your frequency is. So there you go. I did promise there wouldn't be any equations in the presentation, and I'm going to stick to that. So the work's been done. You know, designing LLCs is well established, and there's less degrees of freedom actually than designing a buck converter, but that's a separate topic. I won't go into that right now. Have a quick look at the questions here. Grounds, blah, 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 blah. We'll come back to those questions. All right. How do we design our LLC? Well, we started this process about 2 years ago, and we took the scaling methods and the impedance curves, and we rolled this into our software. So the starting design point for the LLC, you just put in your input voltage, low line, nominal, high line, output voltage, 24 volts, 5 volts on the current. That loads into our software. Now, some of you who have designed LLCs, well, 40 to 60 volt range, yes, you can do it. No, you can't really do it for good efficiency across that whole range. So the LLC has been around for 40 years now is where I first saw it. It didn't get accepted until power factor correction came along. And what power factor correction did is it gave you a very narrow input line range of maybe plus or minus 5% or 10%. That's when the LLC really came into its own. It likes designing just for a narrow range of input. So with a wider range of input like this, it's not necessarily the topology I would choose. It's just one of many that can solve the problem. However, let's go ahead and have a go at this. When you design the LLC, you want to decide what switching frequency you use. And I think I'm a little bit different from a lot of people doing the designs. I like to set up my minimum switching frequency. I know a lot of design processes, they go for where the second resonance is, but to me, the minimum switching frequency is what is going to determine the size of the converter. So here we put into our program that we're going to run this at 200 kilohertz. The default you see was about 144 kilohertz. Why choose 200? Why not? Start somewhere, do a design, iterate. If you can speed up the design process, then you can do iterations to end up with the best solution to the problem. Okay. Let me go live on the software. Hold on a sec here. Struck. Let me go live into our software now. So here is our LLC design in RidleyWorks. We've entered the specifications, as I just showed you. Okay, we enter the frequency. Let's set that to 200 kilohertz. Okay. Then you can choose your topology. So there are a bunch of topologies available in RidleyWorks. And you've got both the half bridge, half wave and full wave to be LLC. And you've got the full bridge, half wave and full wave. You can make the LLC if you want to. And then of course there are all our other topologies here in the program. All right, so we'll choose that topology to be the half bridge. Now we go into the LLC power design. So you click on that button, and then here are the Rosano curves for designing. They're impedance curves, resistance of the tank, input voltage ratio, and it's been so long since I programmed this up, I don't remember what this is, but these are the two sets of curves that you need to design the LLC. Can you do this yourself? Of course you can. You can go download the files that have these curves in them. And that's where we started. There's some changes that we had to make to get them running smoothly, but you know, you have a choice at this point. You could run with what we've done in our software, or you can go reinvent everything we've done and spend the next, it's 2 years for us to get to where we are. These curves are particular for the choice of input range. The impedance curves, of course, are fixed. They will change if you vary the inductor ratio in the LLC. So this is one of your design freedoms. You can choose. Right now we have an inductor ratio of 9. If you look at some of the presentations on the internet of LLC design, some people choose that ratio to be 5. And when you do that, you see these curves changing. So this is something for you to experiment with. It's part of your design optimization. Could we automate it? Absolutely. Are we going to? No, because we like to leave work for the engineer to do. And this is the fun work. So try some different designs, run some simulations, see what's happening. So now, okay, we want to design for 200 kilohertz and for these voltages, and you just click Design LLC.
Designing LLC Converter.
And you can see it looking for the solution here. So it's scanning the curves, looking for the frequency.
Design complete.
And now you
Exporting
see,
simulation files.
so it's found the minimum working frequency, the maximum working frequency, the resonant inductor, the magnetizing inductor, the resonant capacitor, and the transformer turns ratio. So it's a closed form solution to this, looking through the impedance curves and coming up with these numbers. So we had this phase done about a year and a half ago. It's the next step that takes takes all the time. And if you try to reproduce this, of course, you'll have the same issue. Once it's been through the design, you can see that there are 5 LT Spice files generated automatically. And we're going to use those to assess our design. So we now jump from RidleyWorks to LT Spice. And then we open up, oops, sorry. Back into LT Spice. We go find the file. Oops, I'm clicking on the wrong button, aren't I? LT Spice. We go find the first file, which is the steady state file. So everything that was done in that design process through Excel has now been ported right out to LT Spice. And now we can run the circuit. And the simulation goes. And you can see the output voltage coming up to regulation. It's supposed to be 24 volts. You see, it missed a little bit. And that's because there's a lot of non-linearities in here. First harmonic analysis doesn't cover everything. But this is where you're coming as an engineer, and you just tweak the frequency a little bit to get this back to the regulation point. Okay, so that simulation is done. If you want to look at resonant currents, you can do that. See, we generated a lot of data here. And now you can look at the resonant waveforms here, which will look familiar to anybody that's doing LLC converters. We can look at the secondary currents. So let's get rid of those other ones. There's the secondary current from one diode and the secondary current from the other diode. Okay. And then this is where the downside of the LLC comes in. These are fairly high peak currents in here, but they're not flowing all the time. They're just flowing some of the time. It's kind of like a flyback converter where it only delivers current to the output for a portion of the time. So those chunks of current have to be much higher. So if you're designing for a wide range, down at low line, you have this efficiency problem here where you're not delivering current for very long. So that's where we go in LT Spice. LT Spice, it's a great free simulator. We don't use it necessarily because it's free, because we have access to lots of simulators, but it does a really good job and it goes fast. You don't really need these specialty programs anymore. LT Spice goes, fast enough for you to think about the circuit while it's running its simulation. We have found over the years that instantaneous simulations, people actually have an aversion to those because they're not sure something's being done. They like to watch a circuit running. It's like looking at your scope, if it just was there and solid all the time and you couldn't change things, it's not very satisfying. Anyway, so there, LT Spice is doing its job. And let's go back into RidleyWorks, which doesn't want to pull up for some reason. There we go. All right, I'm going to go back to presentation because things get sticky when WebEx is running. And excuse me here. All right, so this is what we just did in RidleyWorks with the curves. As I say, you can go get these online. The files are available for you. They're really, really big files, and you're gonna have to work hard on them, or you get them just embedded into RidleyWorks. So there's the LT Spice file we ran. Now, the next thing we do is we bring the LT Spice data back into RidleyWorks because we need to use these waveforms to proceed with the design of the converter. So here's the LLC waveform. Here's the output voltage that we see is overshot a little bit right now. So we got to raise that frequency a little bit to bring this down. That's our control mechanism. So this is the output voltage we're looking at on this waveform. And then this is the resonant inductor current that's been brought back into RidleyWorks here from LT Spice. And we were a little concerned when linking from LT-Spice back to XL. XL is always the nicest place to present waveforms and to process them. But when we run the LLC converter, we're bringing in 500,000 lines of simulation. We actually truncate it down to 500,000 lines of simulation. And surprisingly, XL doesn't seem to care. We've done up to 1.5 million lines of simulation data before, and it just cuts on through it. It doesn't seem to worry about it too much. So now it's nice to look at these waveforms. You can use these for presentation. You can use these to design the next part of your converter. So this is the first the first file that gets kicked out to LT-Spice is just the steady state operation. So it's taking a guess at where it wants the frequency to be, and then it's trying to regulate this voltage. And as you can see, it misses just a little bit, maybe 5%. That's normal. That's just iteration. There's going to be a lot of other things that move the regulation point as well. As you include more detailed losses of the parts, proximity losses, core losses, all of those are going to move the operating point around as well. So that's your engineering job when you're doing these designs. And then let's look at some more waveforms. This is the magnetizing inductor current. So this is what's flowing in the magnetizing inductance of the transformer. Okay, so we're going to need this because we're not building a pure transformer here. We're building a transformer with very deliberate energy storage. So when we design this transformer, it's designed as an inductor. Because those of you who've seen our magnetics presentations know that it's the magnetizing current that saturates the transformer. We need to know where that current's going to go during transients to avoid saturation, to make a right converter. So we're actually designing this as an inductor, and of course it's a transformer at the same time. But it's the same routine as you would do for a flyback converter. And then our secondary currents. Here within RidleyWorks, we plot the two secondaries on top of each other. So you can see you're always looking for a 0 voltage on the primary, and we're looking for 0 current on the secondary. So we want the waveforms to resonate up and then come back down to 0 before we turn on the other side. So that's the next big advantage of the LLC converter. It's 0 voltage on the primary, 0 current on the secondary. And the whole purpose of this kernel design, the good solid design that we're going to frequency scale and voltage scale, is that when you move to high line and you move to a much higher frequency, you want to keep the 0 current switching, because that's the sweet spot of the LLC converter. So that's what those impedance curves are going to do for you. Here's the high line secondary waveforms. So you can see here now there's not much dead time between the two halves of the secondary. So that means you've done a good solid design. If these two are virtually touching each other, then you're getting into the region where it's going to lose 0 current switching. Nothing catastrophic is going to happen, but you're going to see some more ringing. You're going to see some loss of efficiency if you go too deep into that region. But these are all things that you can experiment with. So what have we done so far? We've gone from spec, one single pass design, to the elements of the circuit. That goes into LT-Spice. The LT-Spice results come back into our design program. And we're going to use these waveforms now to design the next components of the circuit. Let me just, hold on a sec. Let me just pause a minute and look at your questions to see if there's anything I can answer here. Let's see, lots of questions. Let's get rid of the unable to hear ones, because we know that's working. For any questions, thanks Nicola for that one. Range of voltage would use half wave versus full wave. It's a device question. You know, which field are you in? How much over voltage do you have to have on your devices? you know, everybody's got a different choice there. There are some serious advantages to full wave in that you clamp the voltages better on the devices. So it can be nice to do that even at fairly low voltages. So, you know, there's no canned answer to that. Maximum power levels to full bridge. I don't know, people are doing this to tens of kilowatts. Of course, as you go up in power, you have to go down a little bit in frequency. Current doubler, I can't answer that question. Maybe somebody else can answer that. Can I do a CLLC? I don't know. I don't know much about this CLLC. When I saw this LLC converter for the second time in my life, it was about 1987 when I was taking graduate courses at Virginia Tech. And we had the LLC, the CLLC, the LCLC, LC, whatever. There were so many different variations. Do they make any difference? I don't know. I don't know. If you haven't actually built them, you can't really answer that. Does LLC design fit for high voltage? Yes, it does, because you get nice clamps on those output devices. So it's actually very useful for high voltage. Remember, my first design was a 6,000 volt output, and we didn't use multipliers. We needed an AC output, so it's straight through the transformer to 6,000. LLC, you can use it for wide input range, but the peak stresses down at low line are going to be very high. So it's not necessarily the best choice, and that's why in the industry we don't see it really applied if you've got a narrow range input. All right, I'll come back to questions later. Somebody is on the organizer here. If I answered the question verbally, can you just, I'll delete them right there. Okay, great, thank you. Can we export our files into PSIM? Why would you? You have to pay for PSIM, you don't have to pay for LT-SPICE. Could it be done? Yes. It would be about 3-4 months of programming to do that. So if somebody wants to fund that, then absolutely you can put it into PSIM. Frankly, these days, the speed advantage of PSIM or Simplest versus LT-SPICE, I don't think that's a factor anymore. And the fact that everybody's got LT-SPICE is very important. So, you know, if somebody wants that done, sure, we can help, but it's going to cost some money to do that and some resources. All right. Dead time between the synchronous FETs, that's something that you tune in your circuit. Okay, in our simulation, we can open up the dead time, reduce the dead time, but you're going to do it in the hardware because that's all a function of the parasitic converters. Sorry, the parasitic parameters on the switches, the diodes, and so on. They will affect the dead time. Don't expect a one-pass design on the subtleties like that. Okay, you have to tune the dead time that you need. Okay, I'll come back to questions later. Otherwise, I'll get stuck on this. Let's move back to the presentation here. So there's our high line where we're looking for that zero current switching. There's a second file that gets kicked out when we do the design, which is our curve tracer. Now, what you get from that, these are outputs from LT-SPICE, which actually trace the curves. This is frequency on this axis, so we're sweeping from the minimum switching frequency to the maximum. And now we're generating the gain curves of the LLC. In most papers, you see these generated with the first harmonic analysis. You can do that if you want to get the nice, easy, smooth curves. Oh, I won't say easy, smooth curves, the nice, smooth curves that you see. What we're generating here is the actual circuit switching. So that's going to include switching losses, diode losses, transformer losses, proximity losses, anything you want, you can regenerate these LLC gain curves. So they're kind of nice to look at. These are actually for different loads. So the bottom curve here in red is for twice full load. And you can see it can't regulate to 24 volts. This one here is full load. And it could regulate up to 28 volts, but of course we're running it at 24. Another part of the design kernel that Nicola Rosano and Sanjaya came up with is you can't design right at this peak. because you've got no controllability at that point. So you back off a little bit. And I remember a number from Hamish Laird one time. It's about a 30% back off. But this is your divine freedom. How close do you go to the limits? Because you've got to leave some space there for high temperatures. You've got to leave, what is your true low line? So, you design so you're going to be above this resonance, but you got to have some controllability in here. So that's what those curve traces are about. We could write all kinds of app notes and things about how you do these. You can see here we have a bit of a sharp kink in the curve. That just means you have to sweep it slower in LT space. So no, when you're sitting in a meeting, you just run it really, really slowly. But during these curves, it's actually simulating the converter all the way. It's a real simulation with any parasitics you want to include, and it's giving you your real life LLC gain curves. Okay, great. Next thing we have to worry about is transformer design. Let's look at some hardware here now. I can't see my picture for some reason. Okay, this is an actual converter, an LLC converter. So you see here, this is a 300 watt LLC converter. This is another 300 watt, that's another 300 watt. And basically when you look at the boards at the final designs, you only see one thing, and that is magnetics. Okay, so choosing the circuit element is step one. That's the easy bit. Designing the magnetics themselves is step two. That's where it gets more complicated, but that's the meat of the problem here. So like everything in power electronics, it's all about the magnetics. Control is control, and yes, that's important, but we can control almost anything these days. Magnetics are what you need. So I'm sorry, semiconductor people out there, I like to think these days that they're FETs and this type of GaN and that type of silicon carbide is where it's at. You've done such a great job. That's no longer the limiting factor in designing converters. So the design, the hardcore design, the good designs separated from the bad designs are determined by the magnetics. So here we can see the LLC transformer, and as I mentioned before, I design it as an inductance because there's going to be transients in there. You could design it as a transformer if you wanted to. It's really the same thing. But there's a primary value of the inductance, that's your magnetizing that you choose. There's a peak current that's going to see during the simulation. So as you know, you've got the saturation equation of the inductance. That's what you have to satisfy. So you do a bunch of simulations, you find out what's that worst case current going to be. And then you say, okay, let's set the current limiting. Not the current limiting. Let's set the size of the core and the number of turns we put on to satisfy this equation. It goes in deeper, of course. It tells you the core gap that's going to be in there, the AL value of the core. And you can put any cores you like in here. We have a library of about 200. You can add your own cores. Then you go into the core material. Right now we're choosing a PC95. The losses are fairly high for a 100 watt converter, about 0.9 watts in the core. So what that means you would do is that, well, you'd probably use a little bit of less core material and add more turns, or stay with the same core material, the same physical core size, and then add some turns. So you actually back off on the operating delta B. That will cut down the losses in the core. Remember now, this is a core that's going at 200 kilohertz. The delta P is 0.2. That's a pretty big flux swing at 200 kilohertz. Okay, so that's why you're seeing these higher losses involved here. And all of this, of course, is built into our software. You can compare one core type with another core type to compare losses, and you won't see this in anybody's data book because they won't compare the different manufacturers of core materials. Anyway, core loss is a bit high. I would add a few more turns to this probably. Check the winding loss first, see if we got any kind of balance in here before moving on. And let's go on to the next level of the design. you're inside the magnetics now and you have choices. You can design it with magnet wire. You can design it with triple insulated wire. And here you can see we've actually chosen to use foil in this transformer. It's only 6 turns on the primary. So foil is an option for designing the transformer. Notice that when you're in foil, given the size of the window, if you wanted to, you could use a 7mm foil. If you click on minimize loss here, you find out that a 4mm foil actually is lower loss in the transformer. So this is one of the anomalies of transformer design. 60 hertz, we used to think, okay, the more copper you put in the window, the lower loss. As you go to high frequency, you get into proximity losses, you often run into this situation where using less copper gives you less dissipation. So you go from a 7mm down to a 4mm. And then we even plot the AC resistance for versus frequency for you in the software. Now we'll look at the secondary design. Same thing there, it's 5 turns. You can use a foil. You could fit in a 12mm foil. It's not worth it because 5mm is lower loss than 12mm. And if you plotted the AC resistance with 12mm and 5mm, you'd find out that 5mm is actually the better foil. Now, in terms of manufacturing, some magnetics manufacturers out there will know that working with 5mm foil is a lot easier than working with 12mm foil. So not only did you make that transformer better with the thinner foil, you made it easier to build. So less materials, it's not so much of a factor, but just the being able to manipulate 12mm foil is a problem. Okay. So thin foil again. Here's another way you could do the secondary. Sometimes on these converters, you'll see foils in here. Sometimes you won't see foils, you'll see LLC wires. So here is a LLC wire structure that you can build in our software. So you choose magnet wire, you choose LLC, and 2 parallel wires actually gives you the lowest loss. So using wire, we get almost the same loss as foil. So now you go to your magnetics vendor and say, hey, is it better to use 2 strands of LLC or is it better to use a foil from your point of view? Maybe you can try both. Here we let you compare. So the red curve here is LLC and the blue curve here is foil. Down at DC, the foil wins. At 100 kilohertz, the LLC wire wins. And of course, in this secondary, we have a little bit of DC because it's a center tap secondary, and we have some AC as well. They're kind of balanced between the two. So we got 2 amps of DC, 6 amps of AC. So you can't really tell which one's going to win until you split up the harmonics of the main waveform to see which comes in. But there's lots of options for winding design. You can use foils, you can use wires, you can use LLC wires, you can use flat foils, you can try those. They don't usually work well, but sometimes I'll see people use those to try and create leakage. That's our transformer design. I'm going to peek here to see how we have some transformer questions. There's a lot of questions today, which is good, but slows me down a bit. Inductor ratios. Okay, there was a question about how you choose the inductor ratio. So basically, I don't know the answer, and I would imagine for every application it comes out differently. What I've done over the last couple of years, if you look at every presentation out there, you will see inductor ratios going as low as 3:1 and as high as about 10:1. So that's looking at the experience of the industry. My intuition is that about a 9:1 ratio is right, but hey, this is your design freedom. Could we iterate the design 10 times and scan through those? Of course we would, but then we take away all your fun. So we're not going to do that. So try the different ratios, see what you get. And you never know the answer until you've chosen the ratio. That just gives you circuit waveforms, but then you go try to build it. And it's not till you build it and you get down to the details of the wires, you can tell which one was the right ratio there. So there's lots of questions. Can you use GaN FETs for the sync FETs on the secondary side? Absolutely. You can use GaN FETs, you can use silicon carbide FETs, you can use any FETs that you like. Magnetizing inductance, leakage inductance ratio, we set it at 9 as default. If you want to move from there, move from there. Lots of questions on inductor ratios. There's no canned answer. And if you look at all the references on that, you're going to say, well, everybody disagrees on this. So you're free to disagree as well. Okay. All right, we'll come back to some more of the questions in a bit. What about the resonant inductor? So the resonant inductor, it's a two-step process. You know from the circuit design what value inductance that you want, but you're also going to get some inductance from the transformer leakage. So one approach to designing LLCs is to put all that resonant inductor into the leakage inductance. The more common approach I see for the higher efficiency designs is they build the transformer the best way they can build it, measure the leakage at the frequency you want to resonate at, add a little bit of trim inductance around that. So in this example, we had about 100 nanohenries on leakage. It's only a 6-turn primary, and you need 400 nanohenries more of the trim inductance on there. So again, looking at the hardware here, you can see there's a transformer there with its leakage, then another inductor is added to create the actual resonant inductance that you want. Different requirements for doing transformers and inductors, so it's often good to split the two out. This happens with the phase shifted bridge as well. I see designs where they put all the inductance into the transformer, then I see designs where people have added a bit more inductance outside to extend the zero voltage switching range. So that's what we're doing with the resonant inductor. It's a pretty small core. It's not doing a lot. And core materials, again, same core materials, you're going through a big flux swing again in the inductor. It's pretty high current in this one, 25, 30 amps. That's the low line case. That's the problem with a wide range for the LLC. You can't cover that low line without incurring these big peak currents in the circuit. Okay. And we'll go through the winding design. On this one here, 4 turns on an inductor. I mean, we're doing low voltage input. That's why it's coming out with the low turns counts. That's why foil comes in as the winner in this case. Notice here, you could use a 12 mil. The lowest loss design is 3.6 mil. Okay, so they're all coming in for the foil that we use. It's kind of interesting. If you're switching a few hundred kilohertz, there's a whole bunch of standard foils that you can buy from manufacturers, and they kind of start around 7 mils is a very popular one, 5 mils, 4 mils, and so on. That's because that's what we need. Okay, we need to go quite a bit less than the skin depth thickness. We go quite a bit smaller than that because we've got a big stack of foil here. We've got 4 layers of foil here. So we're getting deep into proximity losses. And then this is the AC resistance from RidleyWorks. Somebody asked the question, by the way, how accurate are the losses in the magnetics? Well, they're pretty darn good. If you're not doing proximity loss, you're not even in the ballpark. So we go in, we solve Dowell's equations, and we plot the AC resistance versus frequency, and we use this AC resistance when we do the calculations of loss. Okay, so this is using Dowell's equations. Like if we get time at the end, I'll show you this in the software as well, and show you the equations that we use. One other thing we're doing, by the way, is whenever we generate the AC resistance of the windings on the different inductors and the transformers, primary and secondary, we generate a circuit model for it as well. So this is a 5th order matching network, and you can see on the curve here we're plotting the losses of this network versus the losses calculated from Dowell's. So now we have a simulation circuit for the magnetics that we can use. So we get very direct proximity loss results straight out of LT Spice. So that's one of the things we've worked really, really hard on over the last 5 years to get that running. Not too many people out there doing this yet because it's a complex topic. We're trying to make it easy for you by giving you the models. We fully automated these models. But of course, if you want to go reinvent the wheel and write your own software instead of buying some, then this is a big, big job. You know, you're taking months or years to understand this topic properly and then program it yourself. So I do encourage you to invest a little bit in software that does this. So here we've done this for the winding. Now when we go to our next level of design, so we've done our first level with the component values, then we've gone in deep. Okay, what kind of windings, what kind of cores, what kind of materials you're going to use. You're going to go back and you're going to simulate that again. So that gets to our next circuit here. So this is our next, this is a fairly deep level simulation of this circuit. We've got a resonant inductor and it's got a DC resistance. It's got proximity loss. It's got core loss. For the PC95, it's got a core loss model in here. You've got a core loss model in the transformer. You've got the proximity losses in the transformer, primary, and then the two secondaries. So every one of these little circuit models here is going to simulate the proximity loss as you go through the simulation. So you don't have to go into a post-analysis, what were the harmonics, solving Dow's equations. LT Spice does all the hard work for you as you go. So it's an amazing program for doing that. And you know, one of our concerns, I'm really getting off topic from the LLC here, but it's very important because we've got high frequency circulating currents. If you don't do proximity loss, you're going to miss by a mile. Have to do this level of analysis. When you do it, you kind of beat up on LT Spice a little bit. You've got 34 extra inductors in the simulation. So there's 5 here, 5 here, 5 here, 5 here. 7 more here in the core loss model, 7 more here in this core loss model. So you've got 34 extra inductors in the simulation circuit. Fortunately, LT Spice doesn't simulate as a matrix. It simulates as a sparse matrix, so it doesn't go up with the number of energy storage elements squared. It goes up more linearly. And for some reason, it seems to burn through this model with all these extra loss characteristics, maybe at half the speed of the full circuit. So it's surprisingly good at this, which again caught me by surprise how well it will simulate the proximity losses for you in here. I don't have time here to really talk about control. I see we're almost out of time, and we've got to get back to questions. But the control of the LLC, there are no closed form equations for the LLC. So you can dig in, you can find some theses on this, but they are very much numerically driven. So our approach to the LLC these days is like, well, you know, don't kill yourself suffering through equations and somebody's dissertation. Just take an analyzer. This is what you do in the lab. You take our Ridley box or you take our AP310 or whatever device you might have. We have built that emulator inside LT Spice. So you just sweep through the frequencies, you put it through this frequency modulation device here. So you're modulating the frequency of the switching, and then you're measuring the stimulus to the output and making measurements of control to outputs of the LLC converter. And academics, you all love the control of the LLC because it's really, really complex and it's really, really changeable, and you can write papers until the cows come home. Sorry, English expression there. I don't know if it's American as well. Anyway, here's our Ridley box emulator that you can sweep the circuit without knowing anything about the small signal models. So you're just measuring it as you would in the lab. And then when we look at the kind of curves that we get, this is our third output file, by the way. So you have the steady state, you have the curve tracer, Now you have the power stage sweep file that we generate. And then this is how we generated these curves of the control transfer function. So the LLC, fascinating animal. You can see there's an LC filter in here of some kind. And the phase goes down not just to minus 180 for the LC filter, it goes beyond that. So we know that there's a right half plane 0, maybe more than one. I don't know, I don't really care actually. I just know there's a lot of phase delay here. As you go from high line, which is the red curve, to nominal line to low line, which is yellow is the curve. The resonant frequency shifts. Okay, that means you're getting an effective bigger inductor. It's just like a flyback. Going down to low line, you get a bigger effective inductance. So the resonant frequency shifts, and the right half plane 0 frequency also comes down at low line as well. So it's got all the fun of the flyback, the moving LC filters. It's got a moving gain here too, and it's quite a substantial move. And now this gets us back to the gain curves of the LLC, where it's really steep when you're near the peak, and then it flattens out as you get to that second resonance. So that's reflected in this part of the curve here. So this is an entire topic unto itself. And then, of course, you're only just starting when you look at the control to output of the LLC. What a lot of people are doing these days is actually putting current mode on the LLC. So again, another whole topic to jump into there. Fascinating. It's the right way to do it. You should use current mode. How you implement that, well, maybe Nicola will come back in and do a LLC control webinar for us one day. But it's very much a moving target. People are changing their views of this. Notice, by the way, the resonant frequency of control to output is quite high. Here it's close to 20 kilohertz. It's not 2 orders of magnitude away from the switching frequency. It's only 1 order of magnitude away. Okay, and that's because it's a tiny inductor, the resonant inductor, ringing with the output cap. So it's a much smaller inductor than you would have if you had a DC to DC PWM converter. So there you go on that. Okay, we're about 1 hour here. I'm going to go through and answer as many questions as I can. And while I start answering questions, let's see if I can launch a poll. Launch. There. Select a poll. We plan on doing a lot more webinars. So if you could answer that poll, tell us what you'd like to see next. Here's a list, and if you have some others. And while you're filling out that poll, let's see. I've got a huge stack of questions here. Haha, that's good. Nicola Rosano, Nicola has fed the question. For any question or objections, contact Ray. And I think what he's referring to is there are some people out there who object to the scaling method. Well, if you don't want to use it, don't use it. Works for me, works for everybody else I know that's using it. Is it academically sound? Absolutely. Can I prove that? No, I'm not interested. It just works. So let's not worry about that. Input output grounds, that's entirely your system that requires that. New to power electronics. The simulation files I'm showing you here don't have the feedback loop, but of course we have to have tight regulation on our LLC converter. There is a feedback loop. There's a 5th file that we put out from RidleyWorks, which is the closed loop around the converter. We have not fully automated that yet. Okay. Does the load influence the resonant frequency? Sort of, yes. Can you have access to the LT Spice file? Get a copy of RidleyWorks. It's not expensive. That's got all the files that you need. And we're going to be, sorry, that was gone. What is the meaning of purple and green vertical bars? I have no idea what you're asking there, Tony. Let's get rid of that question. We have to go too far back. Yeah, secondary side current in the real LL circuit. You see variations in magnitude from cycle to cycle. I'm assuming you mean from one half cycle to the other. So that would be a mismatch in winding the transformer and getting different leakages, primary and secondary. So you're going to see it bounce up and down on the two half cycles. Try to get rid of that if you can by winding the transformer a little better. Measure those leakages carefully at full frequency range. Make sure they're matched at the frequency you're running. Okay. Let's close the poll. By the way, on the poll, 45% of you want magnetics. There you go. That's good. Control is next. Control measurement. Looks like you all know how to do that. Body plots and LT spice topologies. Okay, magnetics as it is. Gotcha. Thank you. Okay. Hopefully you can see our screen again now. Is the screen showing up, organizers? Okay, great. Application, any voltage ratio you can deal with with LLC. I mean, the fact that you've got, you know, more sine waves going on in the circuit, it's actually better for higher voltages than a square wave would be. Ron, how do you bring LT Spice waveforms back to RidleyWorks? That's in the manual. It's basically, you have to save the file as a text file, go into RidleyWorks, click import, it brings them in. So that's easy to do. If you don't have zero current switched on the secondary, you're going to lose some efficiency. Sure. Build it, try it. Nobody can answer these questions unless we're into your specific converter, your specific operating condition. You know, that's when things start going different. You have to worry about if I'm not going to do zero current switching, how deep into non-zero current switching are you going to go? How much do you have to deal with ringing? How much snubbing do you have to put on? How much do you have to oversize the secondary diodes or the secondary rectifiers? It's a very complex question to ask, but you know, what we're giving you here is, okay, this is how you design, boom, a solid design coming in through the scaling methods. Move it around, that's what engineers do. Try these different things, okay, simulation and of course in hardware. Hardware is everything on this. Type of compensation, well, current mode, that's all I can say to that. Unless you can accept slow response, doing a voltage mode control of the LLC is a struggle. All right, some people will operate their LLC right at the resonance. They don't care about controllability. They just want efficiency. They're not trying to regulate the output voltage. They're regulating the input. Sure, you can do that. Can the half-wave topology saturate the transformer? Any topology can saturate the transformer. Okay, it's full bridge, half bridge, AC coupled, there'll be transients. If you don't put enough turns on the transformer, saturation comes into play, of course. Can you use it for low voltages? Yes, people are using LLC converters for sub 1 volt output. Okay, so it's very much comes into play on the point of load for processors. You can always regulate very light load. You may need to come in with some different control algorithms to do that. Where in automotive industry would we use LLC? Well, if you read the literature on LLC, everybody builds an LLC. Nobody would want to build anything different. But I showed you this particular LLC converter here. This is a 900 watt design that was built with 3 times 300 watts. You don't have to do it that way. There's a very similar application at 750 watts, where this has got 2 parallel transformers on the output here. And it's my good old favorite converter. It's a 2-switch forward. Okay. Same kind of application, about 1 kilowatt. Same kind of efficiency. One of them is a lot easier to build than the other. The 2-switch forward interleaved is better than an LLC. Should you build an LLC? If you're in a hurry, no. There's many other, I'm not even trying to answer, is this the right topology to use? It is a topology to use. It is turning out to be the topology of choice for industry where you've got a pre-regulated input. Okay. Control is more complex, such that most of the applications we see go to digital control. Do you want to go there? Do you want your life to be easier? So automotive industry, you should certainly be looking at LLC, but if you can get by with $1 and a boost, use $1 and a boost. Life is easy, and you want it to be solid and rugged and easy. Low voltages, yes. GaN FETs, yes, you can use GaN FETs. Is there a minimum load? There's lots of papers on light load for LLC, doing PWM modulation as well. Would I design, if one wanted to design an LLC for 400 kilohertz on 100 kilowatts, I don't know why anyone would want to do that. I think you'd be nuts to design 400 kilohertz on 100 kilowatts. I mean, why? It's just to say maybe you've done it, but no, 100 kilowatts, you're not going to switch at 400 kilohertz. It's just not going to happen, in my experience. Calculation of the design circuit is all done through Nicola Rosano's impedance curves and scaling techniques. Watch our previous webinar on LLC design. You'll find all that. And then you'll find a link to the book as well that does that. Red blue curves. I think you're talking, Matthew Kalicharan, you're talking about the proximity losses. You're solving Dowell's equations for foils, wires, Litz wires, and so on, and comparing the results. Is there a reference for Litz wire for transforming new LLC designers? You try Litz, put it in there, see if it works. If it doesn't work, don't use Litz. Do a calculation in our software first to steer you in the right kind of direction. Okay. Low voltage, no problem. Can you use MATLAB Simulink? Sure, why would you? We've got it made much easier than that. Okay, you're just reinventing the wheel there. PSIM has a very, very complex design algorithm for LLC. I don't understand what they're doing. They want you to calculate the Q and this and this and this, and you just get wrapped around the axle. I don't know why that is so complex in there. Probably because they're not power designers, they're simulation people. How to simulate silicon carbide? You just put in the parameters of the silicon carbide FET or the GaN FETs, and off you go. We have buttons to do that inside RidleyWorks. How about gap field loss when using foil? Don't put the foil near the gap, and then you don't have a gap field loss. And we can cover that in a future magnetics seminar. But yeah, don't get your gap near the foil. It's always that answer. Split primaries, split secondaries. We do that we allow you to split the primary. There's so many permutations that can we do everything? No, we can't do everything in there, but you can approximate it. If you've got our software and you know something about transformers, you're going to say, well, a split primary is really the same as a split secondary. So you can fake it a little bit. You need some engineering judgment to go in there. There's so many different layouts of a transformer. We can't possibly synthesize all of those. If you have a desired frequency range, how do you go about it? I don't know, that's kind of the output is the frequency range. When you're done, you choose the minimum, you end up with what the maximum has to be. So you can't really start with that frequency range and then go backwards the other way. If you want narrow frequency range, just restrict your input voltage range. How do you develop PSpice models? Well, I don't know why you'd use PSpice. It's expensive. Use LTSpice. Sorry. Right, low inductor ratio increases reactive current, of course. I'm sure there are some gains with low inductor ratio. I don't know what they are, but the designs I see are mostly pushing to that high inductor ratio these days, and 9 seems to be a magic number on that. DAB, Is it attractive at low line voltage compared to LLC? Well, DAB is a player as well. Be aware if you do dual active bridge, you are in digital control. That's it. But there will be issues with the DAB as well. I mean, no converter is perfect, otherwise we'd all be using the same one. Remember now, as I just showed you, the old converter from 50 years ago, a forward converter, it's still competitive. So there's no need to do these fancy things, but you should know what you're getting into if you try. Is the LLC suitable for low input voltage? Well, you've got resonant primary currents. If your range is small, the resonant currents are reasonable. If your range is wide, you're going to have some really big input currents. All right, so it's about the range of input voltage, not the absolute value that counts. Capacitor charging. That's tough because if you're capacitor charging, you've got a big range operation again. You're starting at low voltage and you've got to charge up to full voltage. So you're designing an LLC that's got to go over a big range. There's lots of other ways of doing zero voltage switching. It's not just the LLC that has that. So look into those too. Power range for half bridge and full bridge LLC. It's the same as hard switched. We see the half bridge going up to about 500 watts. And then after that, the full bridge takes over. Does it need to? No. Sometimes you may do two half bridges in parallel with each other, but it's somewhere around that 500 watt range for most of us. Planar transformer, it's the same. The planar transformer it's just a transformer. It's a different way of laying the windings. You still need the same turns count. You still need the magnetizing. You still need the same leakage. It doesn't matter whether it's planar or whether it's a standard transformer. It's the same kind of design. And we'll talk about that in a future webinar. Can I have access to the LT Spice models? Get a copy of our software, you're all set. If you're a student, there's a student copy as well. How do we calculate the efficiency? Just look at each component. LT Spice is where I like to do that, quite honestly, because it does proximity loss like nothing else. It does all the harmonics at the same time on proximity loss. Nobody does that in any closed form way. They've tried, but they're not going to get there for an LLC converter. So efficiency, you just dig into that LT Spice model to get that. Shifting gain curve looks familiar. Yes, it does. I don't know what this is about. Not answering P-Spice and planar transformer questions. I don't know what you're talking about there. We do planars all the time. We use the Ridley box and we use the AP analyzer for research. It's in aerospace. NASA have them, you know. And we're talking about P-Spice. I'm just not interested in P-Spice, quite honestly. It's too expensive. And it's harder to use, but if you take the LT Spice model, you can easily put them into P-Spice. We're not going to automate that for you. Okay, you've got to do that work yourself. So sorry, but if you want P-Spice, just get the files from LT Spice. There are ways to port that into P-Spice. Can you explain the statement that LLC converter has lesser degrees of freedom than a buck converter? Okay, well, you want to design it for zero voltage primary, zero current secondary. That really constrains you. And then you've only got the ratio of the magnetizing and the resonant inductor to play with at that point. And then you're kind of locked in. For a buck converter, the degrees of freedom you have, well, it used to be a buck converter would have 10% ripple. Now it's 20%, sometimes it's 30%. But we are seeing buck converters now with 200% ripple on the output, and they turn out denser than anything else. So you've got this huge variation range in the buck converter that you don't have in an LLC. LLC looks like it's a really difficult converter and more opportunities to change things, but actually you don't. You're very constrained. Buck converter is wide open for design. So that's kind of cool about it. Magnetics P-Spice simulation. I keep answering the same question here. If you want the P-Spice simulation, get our models from LT Spice, then you're all set. Please move away from LT Spice. Well, that's one out of 10,000 is saying that. LT Spice has, as of the last count, they're getting about 40,000 downloads per month. Okay, free LT Spice is the future. I'm not going to pay for my Spice, sorry. Can I use LSE for low voltages? No problem. Grounds. Half bridge plus clamping diodes. No, we won't implement that in RidleyWorks because one, I haven't used them. You're going to do it in your hardware, quite honestly. Do we offer holiday pricing on the Ridley box? Yes, it's the same as the rest of the year, and it's very aggressively priced. If you add up the cost of the computer, the picoscope, and the software, it's more than we're selling. All right, software is the same price for everybody. Rosano graphs, yeah, I refer to the curves of Rosano curves as well. How to find soft switching? Well, it just happens when you design it in the right place. Getting through there. Still got a lot of questions to go. All right, somebody said a 220 nanofarad with 516 nanohenry inductor, as quite accurately pointing out, it's a 470 kilohertz resonant frequency. But remember now, at low line, you've got the resonant frequency, and then you got to pause, and then you switch again. So the resonant frequency is higher than the actual switching frequency. All right, so you're going to see that those L and the C don't correspond to the switching frequency. They correspond to the resonant frequency of the tank. That's different. Loss equations, I don't know what you mean. Okay. How are the losses distributed in the LLC? Well, look at the hardware. Here's your magnetics. Here's your semiconductor. Who do you think is putting out the most heat? Okay. The beauty of modern converters is that the heat has disappeared from the FETs, either the primary FETs or the secondary synchronous rectifier FETs. The heat is now aiming at the magnetics. If those magnetics weren't getting hot, they would have made them smaller. So the focus of everybody's design these days is magnetics. Okay, low input voltages, we answered that one. Wide output voltage range, no, not really, because it's the same as a wide input voltage range. Can you be multiple outputs of the voltage here? Yeah, this is the cool thing about the LLC. If you want to do a multi-output LLC, you just add another winding on it, another rectifier. It's just like a flyback. Add as many outputs as you like. You will not find many papers about multiple output converters, whether it's a flyback or an LLC or a forward converter. Nobody writes multiple output papers. And they don't do that because they don't behave very well. The cross-regulation from one output to the other is not what you would like it to be. But the LLC is very much suited for multiple outputs because you're going straight from the transformer into the output cap. There's no L in the way. So that makes it very happy to do multiple outputs. So yeah, you can plan on that. How does the proximity loss model work for PCB planers? Well, we do PCB planers foils for the inductors. We haven't done the transformers yet. Will we do that? I don't know. It's hard work doing the planers. To be honest, I'm not a big fan of planers. You just don't get enough copper, and arranging the wires on this side and all that FR4 material is not a great solution. But that's a topic for a magnetics webinar. Can you do constant frequency LLC? People do constant frequency LLC, but they don't regulate at the same time. Can you modulate inductors? Yes, you can, but that becomes lossy. Best way to current share LLC. It's hard. It's hard when you do synchronous rectifier secondary and then you put the two in parallel. You can get situations where one LLC starts running backwards. So current sharing can be a little difficult between them. Getting into digital control at that point, really. Is it challenging to parallel the LLC? Yes, it is. Is it done? Yes, it is. So everything's a challenge. LLC is a challenge, absolutely. Can I use simplest of magnetics design? No, it's a simulator. Okay, they've hacked away at magnetics. They haven't done a very good job at it. But you don't look for your simulator to do the design of the magnetics. Okay, you look for a magnetics person to design the magnetics. So Simplest has a sort of magnetics designer in there, but it's not anywhere near as sophisticated as ours. Could you use our models for simulating the proximity loss afterwards? Absolutely. Are we going to leak Simplest? No, because it's just not enough user base, quite honestly. Do we support different devices? Yes, we do, but we don't list them as a specific device. Go get the parameters, put them into the software, you're all set. Blue Origin used LT Spice. Boeing used P-Spice, correct. I can tell you that Jet Propulsion Labs uses LT Spice. And let's not, this is ridiculous. Blue Origin used LT Spice, rocket malfunction several times. That's a ridiculous comparison. It didn't crash because they used LT Spice. All right, anyway. Use whichever one you like. If your company wants to buy P-Spice for all your engineers and spend all the money, that's great. Then just port the models to there. Right, so if you want to reduce the frequency range, as Nicola Rosano pointed out, you go for a lower ratio of the inductors, but then of course you've got higher stresses. So there's always a trade-off in choosing that ratio. Can a planar design work for LLC? Yes, it can. Is it the best? Often not. P-Spice is now $4,000 for 4 licenses. Well, that's a no-no. For LLC, the input voltage range should be narrow. So that's when the LLC took off, was when people pre-regulated the input range. Okay. How can you do current mode control of the LLC? Good question. Go look up some papers on that. People are doing current mode. They've got little current sensors in there. They actually put 2 caps in, and they look at the voltage on the cap, and they do some integrators. They build current observers, and they get the dynamics of current mode control. It's really, really interesting. Nobody has begun to model current mode control, and you won't. You'll just simulate it in space with an emulator for the network analyzer. But current mode control, yeah. It's not like you can't do a half bridge with current mode. You can do AC current mode in a half bridge. So it's a deep topic. It really is. That's why we didn't do too much on the control here. These sessions are great. Thank you, Gregory, for that. I like the Q&A too. These people are listening. All right, we've still got 200 of you in the room. I've got 12 more questions to go. Can you design a variable output power supply in RidleyWorks? Yes, you can. Is it direct? No, it's not. You design it as a fixed output, and then you just run it at lower outputs after you fix the design value. So yes, we do that all the time. How can I optimize my magnetics design for proximity effects? Well, you do multiple designs. You know, we looked at a while, can we do all the choices for you? So we could go, can we go foil wire, multi-strand wire, Litz wire, and optimize the proximity losses? We could loop through that and find the answer, but then you never learn anything. I prefer to choose the wires and the type of winding in conjunction with knowing about how you're going to put this together, so that you don't blindly choose foil because it comes out better. You have to know the price of foil at the same time. Same thing with lits. If it doesn't make a big difference, well, don't use it because it's more expensive. All right, so optimization, you know, the artificial intelligence crowd want to take away your whole design job. We're not about that. We put a certain level of optimization in there, like choosing foil thickness. We automate that for you, but we're not going to step through every single permutation and you just click the button and walk away and you come back to a design. That's not engineering. That's just, it's not going to work because it's just not going to include all the practicalities at this point. Forgot what I was saying there, but never mind. Is there a way to model the impact of heating temperature on the magnetics for LLC? Yes, there is. We do let you put in different data sets for the temperature of the core and the core loss. We haven't put in the conductivity of copper at this point. It would be easy to do, but haven't done that yet. Can the LLC be protected easily? Short circuit? Well, it actually has an inherent protection in it because it's capacitor coupled and you're processing resonant tank waveforms. There's an impedance of that tank that does give you short circuit protection. So it's not like a full bridge where you got all that input power available and then suppose your output inductor saturates and you're just dumping energy from input to output and it runs away like crazy, or you saturate the transformer. So protection of the PWM converters is tough. Short circuit, yeah, it will have some short circuit protection, so that's one of the advantages. If it wasn't tough and rugged, you wouldn't see so many of them in very high reliability applications. So yeah, it's kind of nice. Synchronization, multiple outputs in LLC, that's a tough one. I don't know how people are doing that. There's probably a million different ways to attack that. I don't know what DSpace is, but that's not where we design as a platform. I'm sure you can design things anywhere. Those of you who, you know, we run our design in Excel because Excel is really, really good at plotting. There's about 10,000 equations in our design processes now. It's growing all the time. It doesn't really matter which platform you use. What matters is who's got the time to load the equations in. So that's the hard part. Capacitor advice for the high secondary peak currents. People are using multi-layer ceramics in conjunction with, you know, organic electrolytics. So if you look at this design here, here's the electrolytics, and then down on the board you see some multi-layer ceramics. So it's a combination of caps, as in any high ripple application. So everybody's got a different solution to that. Battery charging application, I think it's fine for battery charging, quite honestly. I don't see why you wouldn't do that. You just put a little filter. If you see the pulsing, you put a cap across it. So the cap absorbs the pulses of current, and then the battery doesn't see that. And this happens at low frequency charging as well. Frenetic, yeah, they tried to do AI for magnetics, but with limited success, I would say, but they're still trying. Tips for compensating an LLC converter. That'll be next time, okay? Is the dual active bridge a better choice for large gain than the LLC? Maybe it's better for a large range of gain, but for large gain, you could use either of those. So I think people are trying to answer that question now. Which one is the better? And every application has come out differently. Flyback, input current. Yeah, input current is the right place to sense the current for the LLC. Yes, it is. You want to do it on the low current side in general, so it goes in series with the transformer. But look this up on some of the app notes. They got some really, really clever sensing mechanisms for looking at the input current. PWM ICs, I never remember which one. You want to go analog or digital is the first thing to answer there. We've had this discussion several times on our Facebook group. So I do encourage you to come there and get answers to those questions. Input current, yes, yes. Half bridges have an average sine wave voltage of VNO2. Yes, it does. It's half a dozen of one and 6 of the other when doing half bridge versus full bridge. So, you know, can't answer that for every topology. Okay, so thank yous. LLC for ultrasonic driver. Well, Charles Jenkins asked the question, can I use LLC for ultrasonic driver? Well, that was my very first project. No output rectification. We were running at 20 kilohertz. We used an LLC. It didn't blow up very often on the switches, so sure, try an LLC for an ultrasonic driver. Is it the right answer? I don't know. I'd have to know more about the specs for that. So there you go. I've got everybody's questions. Thank you for the feedback on the next topology. Buy our products, that keeps the webinars going. We do frequency response analysis like no one else. This is the super high-end frequency response analysis, is the AP310, very much for the aerospace people. RidleyWorks is our you know, our working man's frequency response analyzer that just happens to have a 4-channel scope and a computer in it as well. So you can't beat the value of this one if you're looking at other options out there. So this is our high-end one. This is our high-end with lots of other stuff in it. They both do a really good job. This one will sweep faster and give you more dynamic range and have full calibration. We run workshops if you want to learn more from us. Our next workshop that has space is in March here in Camarillo. December 1 is booked up with a wait list, and then we got another one in June. We will be coming back to Europe at some point during the next year. We just haven't scheduled that next. And then those of you that want free stuff, everybody wants free stuff. There's a free book on current mode control. Download that. If you just click on your PDF file, it will take you to the web page to do the download. Do come and join our Facebook group. Oops. I know everybody hates Facebook, but it's the only place where there's any active discussion going on of power supply design. And we have some very, very lively discussions on power electronics here. There's 6,000 very experienced engineers on our Facebook group talking about GaN. We talk about hydrogen quite a bit, artificial intelligence, dual active bridge, Texas Instruments controllers, old patents on soft switching and other things, transformers. It's the most active group in the world. Yes, it's Facebook, but they do groups better than anybody else. So try to overcome your dislike of Facebook if you have that problem and join the group, and you'll really get a lot out of it. So the link is there in your presentation material to find that. Okay, thank you all very much. Rafael Gonzalez, any LLC workshop? I don't know, come work for us for 6 months and you can help us develop it. Okay, Rafael, that will be fun. So let's have a go at that. But yes, we absolutely plan to do the LLC workshop. We got the preliminary stuff. The first thing we had to do was get RidleyWorks doing it for us. And that was harder work than we imagined. But there you go. Thank you all for coming. I really appreciate it. Feel free to send us any feedback. You will get a follow-up email on this, and in about 4 or 5 days, this will all be recorded and uploaded with the presentation. So I appreciate your attention. Have a great day, and we'll see you next time.